Alright, so a quick little to-do about sound waves. Sound waves are longitudinal waves due to the vibration of an object, just as we discussed in class. The guitar vibrates, or here is a speaker that woofs, 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 woofs as it pushes those air particles, those compressed air particles that we call compressions. Here are rarefactions, and this gives us a wave. Just like from crest to crest gives us a wave, or from trough to trough. Our rarefactions coincide with troughs, and our compressions coincide with crests. The back of the guitar, a hollow body guitar, vibrates back and forth to push these air particles, these compressed air particles, towards your eardrum. They come in here, they bounce off the actual drum, and your brain interprets that as sound. The frequency gives you the pitch, obviously. As noted right here. One thing that came up in discussion, and it's worth mentioning again, is a hollow body guitar gives you a much larger compression here, which would be more amplitude than, say, an electric guitar that's not plugged in, because it's not going to push many particles, because it doesn't have that back wall pushing that all the sound through the hole. It has more vibration in an acoustic guitar, meaning more compressions, meaning more amplitude, more air particles hitting your eardrum, louder volume. Still the same frequency, it's just difference in amplitude or difference in volume. So, first thing, we sort of already talked about that. The key concepts: frequency tells us our pitch. We've been over that and over that. We've talked about, played Mary Had a Little Lamb with our pop bottles, and you can also see that in a guitar, starting with the bottom string, which is actually the top string, the biggest string on the guitar, is a low E, has a 82 hertz as the frequency. That means it has a long wavelength. Let's just do that. I mean, you just can't do this enough. You can say this is a long wavelength, and as we move down the string E, A, D, G, B, E, the wavelength gets smaller and smaller, which would mean, and I know I'm not doing this right in terms of standing waves, and you guys will probably correct me on that, but the point is, I want you to see the wavelength gets shorter and shorter as we move. Whoops, gotta get that even shorter. A perfect wave here. As we move down a shorter wavelength, gives you a higher frequency gives you a higher pitch, so the smallest string on the guitar gives you the highest pitch, the highest frequency. Enough about that. Let's move on. The speed, let me get this stuff out of here, depends on the medium through which it travels, just like with any wave. And you can see here, we had this discussion the other day, I did with somebody, as you change from different mediums, the speed of the wave changes, and it just depends on the medium, right? If we're in carbon dioxide, 259 meters per second. If you look at air, 330 at 0 degrees Celsius, standard STP, and if we jump up to like 20 degrees Celsius, which would be more like room temperature, you jump up to 343. These numbers don't put too much weight in this. I'd usually average 330 or 340, just so that you've got a number. The main idea is that I want you to see that the speed of the wave is consistent throughout the medium if it's at the same temperature. However, as temperature increases, the speed increases, because think about temperature as the movement of particles, the kinetic theory that you talked about in chemistry. So the particles are moving faster, the wave's actually going to go through that material faster, and so you get a faster wave speed. Notice what happens when we go to liquids and then to solids. What happens to the speed? Whoosh! It shoots through the roof. And that's why if you're underwater at the swimming pool, starting to think about spring break already, if somebody's at the other end of the pool and they're just barely tapping on the gutter or on the floor, you can hear it very well at the other end of the pool, because that sound travels a lot better through water than it does through air. And if you were to put your ear against the gutter at the other end of the pool, you're going to hear it even clearer, or technically faster, because it's traveling better through solids than it does through liquids, which is better than traveling through air. And so speed of the wave depends on the medium. Last thing I'll talk about is what you've probably heard about before, and this just sort of puts it all in perspective. The intensity is described as a decibel, okay, and that's how we rate sound intensity. And really what we're talking about is some sort of mix between not only frequency, but also the pressure, or I guess you could think of it as the volume. And so here we see this is our normal hearing range, right around in here. When we get down, 0 decibels is going to be stuff that we cannot hear, or the low end of the threshold of hearing. This is usually where we're talking. Here's where we see music, and so this is where you see, if we get enough intensity, that's where you can shatter that glass that you've seen in all sorts of pictures. One thing that's interesting to note is you've possibly have heard about the old couple where the husband says, or the wife saying, "You don't listen to me anymore," and the husband saying, "Oh, I couldn't hear you." And so lots of times it's just kind of a joke, but in all reality what happens is we lose the top and bottom end of our hearing threshold as we get older. And so what happens is, lots of times those old grandpas are actually being honest that they can't hear these higher pitches, because we lose the high pitches first. And so if you've got this grandma with this high squeaky voice, it may be that actually grandpa doesn't hear her because his ears are not recognizing that high of a frequency. Just like when we blow in a dog whistle, we don't hear it because the pitch is too high. The frequency is outside of our threshold of our hearing range, so we can't hear it. The dog hears it. The dog doesn't like it at all, but we just can't hear it. And so what happens is our eardrums actually diminish and get a little bit weaker and weaker, and our threshold, this creeps in right here, and it may creep in so far that unfortunately you don't hear those high-pitched sounds, whether it's a baby crying or your wife asking you politely to do things. So that's a little bit on sound waves. Hopefully that makes a little bit more sense. We aren't going to spend a whole lot of time talking about it, but I do want to give you some sort of overview so you have a context to think about whenever you're talking about sound.